So let's do an exercise. Okay, so first of all, when is the normal approximation going to be good for a binomial? When's it going to be bad? It's better when p is close to 50% than when p is close to 0 or 100%. It's better the bigger n is. Okay, the larger the number of draws, the better the approximation is. Yes?
So when the distribution is skewed, you said you have to increase the number of draws, right?
Right, the normal approximation is going to, so if we keep p the same at 1%, but we increase the number of draws to 100, then this approximation is getting better. It's still not very good. If we increase the number of draws to 1,000, now we've got 8% versus 7.3%. It's getting better, right? Okay. All right. Typically, the normal approximation to the binomial probability distribution is not terrible if n times p is at least 5 and n times 1 minus p is also at least 5. And if the range of values that you're trying to find the probability for is pretty close to the expected value. If it's out in the tails, if you're trying to find probability of something that's very small probability one way or the other, then the relative error is going to tend to be larger. Okay, let's do a couple of examples. All right, so we've got a box of tickets. There's 14 tickets labeled 1. The rest are labeled 0. We're going to draw 600 times with replacement from that box. And we want to know what's the chance that the sum of those draws is between 388 and 430. So we're drawing 600 times from a 0, 1 box, right? What's the probability distribution of that? Okay, so let's call x this thing that we're trying to find the underlying random variable, the sum of 600 draws from that box. And x has a binomial distribution with parameters n is 600 and p equals what? Right. 10/14ths of the numbers in the box are equal to 1. The rest are equal to 0. Okay. So the actual probability we're trying to find, not the approximation, the actual probability is what? It would be the sum from little x equals 388 up to 430 of what? 600 choose x times 10/14ths to the x times 4/14ths to the 600 minus x, right? That's the actual thing, which is the sum of whatever that is, about 40 some odd, 42 terms, 43 terms. Messy. You're not going to be able to compute 600 choose x. It's going to overflow your calculator. Yep, it's okay. This is not okay. So this is what we'd like to know. It's not practical to calculate it exactly. Instead, we're going to approximate it by the area under the normal curve. In order to do that, we need to turn 388 into standard units and 430 into standard units. Right? Now, we want 388, but we want 388 as a possible outcome. The bin of the probability histogram that includes 388 starts where? 379.5, right? Because this is a binomial, its possible values are the integers. Okay, so we want to convert 379.5 into standard units. How do we do that? Oh, sorry, 387.5. Yeah. Thank you. My no short-term memory at all. Right? Forget it. 387.5. Okay, so to convert this to standard units, we would take, this is 387.5 minus the expected value, which is 600 times 10/14, right? N times P is the expected value. And what's the standard error of this random variable? It's the square root of N times P times 1 minus P. Okay? So this would be, this is now the lower endpoint of the range, adjusting for the what's called the continuity correction, right? We're taking the whole bin that includes the outcome 388. So we're starting at 387.5. And now what's the upper endpoint of the range that we want? It's 430.5. To convert that to standard units, we would have 430.5 minus 600 times 10/14 over the same number, 600 times 10/14 times 4/14. So that would be the upper end point of the range. This is going to give us two numbers, and then we want to find the area under the normal curve for that range. So we can ask our good friend Google to calculate this number for us. It looks like, whoops, 387.5 minus 600 times 10 divided by 14 divided by the square root of 600 times 10/14 times 4/14. Okay, minus 3.71. Is that right? Okay, and then in the other direction, this number just needs to become 430.5. Oops, got an extra 0.5. Okay, 0.174. Okay, so let's go back to the applet. Here's an example of it. We want to go from minus 3.71 up to 0.17. Okay, and that's 56.9%. So the normal approximation of this probability would be 56.9%. Let's see if I can remember that all the way down to here. Okay.